Celestial objects. Celestial objects are any objects outside or above Earth's atmosphere. So that includes the moon, the stars, all of the images on this screen, nebulae, galaxies, stars, black hole. The universe is anything that exists in any place, and there's only one of it. That's why we call it the universe. Uni means one, so there's only one universe that we have any physical evidence of, and thus it contains everything. The Big Bang Theory is the theory that the universe started as a small area of concentrated matter and energy that exploded 10 to 17 billion years ago and has been expanding ever since. This is a visual representation of the Big Bang. Originally, tiny, tiny point of incredibly hot mass and energy, and then very, very quickly, in less than a second, it expanded and started to form the most basic particles, radiation, quarks, antiquarks, electrons. After about 3 minutes, atoms started to appear, helium, lithium, and soon they got fully developed atoms after 300,000 years. You go from helium to more advanced atoms, it takes a long time. After about 1,000 million years, or 1 billion, galaxies formed, and the heavier elements. And finally, right now, about 15 billion years later, we have on Earth thought, culture, DNA. Evidence for the Big Bang, which of course we have to have, otherwise it's not science, is background radiation, for one thing. This is an image of the microwaves. Microwave radiation is spread throughout the entire universe. And when we look into space, we can map where the microwaves are. Some places they're more concentrated, in other places they're more diffuse, which gives us actually a map of that very, very early universe. A second point of evidence for the Big Bang is the Doppler effect. You've heard of the Doppler effect when sound goes past, when like a siren goes past you. The sound changes due to the Doppler effect. If here you've got an object that's moving this way, as it's approaching you, the waves become shortened, which in sound produces a higher pitch, and in light produces a bluish color. When it's moving away from you, it stretches out the wavelengths, producing a red color in light or a lower pitch in sound. This is the full electromagnetic spectrum, from radio waves that are about the size of buildings, they're very large, down to gamma rays on the far end of the spectrum, the highest energy and the shortest wavelength that would actually bump into atomic nuclei. So extremely large to extremely small. Visible light is in the middle, and this is what we get the Roy G. Biv from. In this scale, a protozoa is what the wavelength jumps over. You can bump up and down between these protozoa in visible light. Smaller than a pinpoint, bigger than a molecule. When the wavelength is more stretched out, you're on the redder side of the spectrum, closer to radio, very low energy. And as the lines get closer together, as the wavelength becomes shorter towards the blue and violet end of the spectrum, you get higher energy. Redshift is the shift towards the longer wavelengths of energy. Shows the object is moving away from Earth. The further away the galaxy, the greater the redshift, because they are moving away faster. Almost all galaxies show a redshift, which is proof that the universe is expanding. Edwin Hubble was the first to realize this. He looked up in the galaxies and noticed that all of the galaxies were running away from us, as if, we had done something terrible and they're running away. But in fact, it's simply that we are moving away from them as well. The whole universe is expanding. A close galaxy, here we have spectrum of light. This is the spectrum of light for hydrogen. Hydrogen, when you heat it up, produces a glow in this color. This is when it is right here close to us. However, when we look at slightly distant galaxies, it shifts. This fingerprint, this pattern, shifts to the right towards the red edge of the spectrum. And the further away the galaxy is, the further into the red that fingerprint goes, which is evidence that these galaxies are not only far away, they are moving further away from us. This is one for neon. No, I think this is helium, hydrogen. Hydrogen or helium, I can't remember now. And so it's right here at Earth's surface, close to us. When an object is moving away with that color, with that pattern, it shows a red shift. When it's coming towards us, you get closer towards the blue and purple end of the spectrum. That's a blue shift. This blue shift towards the shorter blue wavelength of energy, shows that an object is moving towards Earth. Some objects are blue shifted on one side and red shifted on the other. This shows that the object is rotating. So here is a spectrum, a fingerprint at rest. When it moves towards us, when an object moves towards us, this pattern moves a little bit to the left, the purplish side. And when it's moving away from us, it moves a little bit to the right, the red side. In terms of structure of the universe, first we have galaxies. These are collections of billions and billions of stars, held together by gravity. Typically, you have over 100 billion stars in a galaxy, and there are over 100 billion galaxies. So there are many, many stars in many different galaxies. We classify galaxies by shape, elliptical, for instance, or irregular, or spiral. The Milky Way is our galaxy. It's a spiral shape and has over 200 billion stars. These are some typical shapes of galaxies. Elliptical, meaning longer, or ovular. Here's more spirals. We have intermediate spirals. We have barred spirals. It's like a bar down the center, and then the spiral comes off the sides. And just irregular, random different shapes. In fact, there's so many different shapes that some people have fun with them. Science. These are all galaxies with odd shapes that end up looking a bit like letters. Stars make up galaxies. They are much smaller than galaxies. And these are some typical sizes, some typical types of stars. The sun, this is to scale. Here would be our sun. The red giant, much larger. One day our sun will become a red giant. And the supergiants, which our sun is never going to be big enough to equal, are much, much larger. Here's a scale drawing of the relative sizes of planets and such in our solar system. Here's Earth. If Earth is this size, the sun doesn't even begin to fit on this picture. Jupiter, much larger. Mercury, Pluto, other gas giants. Now think, if this is Earth to the sun. So if we shrink down Earth to this size, this is the size of the sun. So we shrink down the sun to this size. These are the size of the larger stars. We are a very tiny planet in a very, very big universe. Distances in space are typically, in our solar system, we measure by the astronomical unit. It's the average distance from the Earth to the sun. At 100 miles an hour, it would take us 100 years to go 1 AU. So if we traveled 100 miles per hour, it would take us 100 years to get to the sun. So 100 miles per hour, while fast for a car, is far too slow for space travel. Light year is the distance traveled by light in a year. It measures distance, not time. It is 5,880,000,000,000 miles. 63,000 astronomical units. So a light year is very, very far away. Some sizes. 1 AU is this distance from Earth to the sun. The solar system is about 80 AU. The nearest star is 4.2 light years, 268,000 AU away. This is it, Proxima Centauri. It's a red giant. In this distance, it looks very small, but it is much larger than our sun. Our sun here in the Milky Way galaxy is nowhere near the middle. Here's the bright center. We are far out on it. And the galaxy, the Milky Way, is 80 to 100,000 light years in diameter, depending upon where you measure. The nearest major galaxy, Andromeda, is 2 million light years away, 126.5 billion AU. So if our nearest star is 4.2 light years away, it takes light over 4 years to get here from there. We can't travel at the speed of light, so it would take us a very long time to travel in space. How do we measure distance? Well, here are two options that many people think of. A, we travel there and measure the distance. Or B, we look at objects and use what we know here on Earth to make inferences. Of the two, the answer is B. We can't travel to other places and measure the distance. They are far too far away. We have to make inferences, guesses. We can't travel far in the immense distance of space. Voyager 2, for instance, has been traveling for over 30 years at 35,000 miles per hour. It only just got to the edge of our solar system. So 30 years, and it's not even completely out of our solar system. It will not get to Proxima Centauri in our lifetimes. It will take 80,730 years to get there. So 80,000 years to get to Proxima Centauri, and we don't even know if there's anything interesting there. We're going to be stuck on Earth for a while, learning about other places just from the light that we get from them. So how do we measure that distance? First, we use parallax. Parallax. If you notice, if you ever close one eye and look at something and then close the other eye and look at it, the object seems to move. We can use the same idea here. Earth in January is on this side of the sun. And if we're looking at this red dot against this background of stars, it appears to be over here on the right. But in July, the star is over here on the left. Our point of view changes closer stars' appearance. See, like in this picture, objects that are closer move faster than objects that are further away. You're used to that with seeing cars whiz by. As you drive along the road, you see trees whiz by you. When distant objects like mountains and clouds seem to stay put. So we can measure close items by parallax, but that doesn't get us everything. Luminosity, or brightness of stars, can tell us distance as well. If we know how bright a type of star should be, if it's very dim, it must be far away. And just to give you some scale, each dot on this screen is an entire galaxy containing billions of stars. We are a tiny little dot on the Earth, which is a tiny little dot in our solar system, which is a tiny little dot in one of these tiny little dots on the screen. We are very, very small.